In this video, we're going to look at geometric sequences and series. So a geometric sequence is a sequence of numbers that has a common ratio between all of the terms. So the easiest example to do with a geometric sequence would be the sequence 1, 2, 4, 8, 16, 32, so on, so on, so on. So unlike an arithmetic sequence, where we have a common difference between all of our terms, for a geometric sequence, we have a common ratio. And we can kind of spot the ratio here because to get to each new term, we're multiplying by 2. And it's going to be consistent. And the fact that it's consistent, it means that it will be a common ratio and we'll have a geometric sequence. So the ratio here would be positive 2. Now there are some formulas, some IB formulas that they do give us that helps us find any term in a geometric sequence. So we might be able to find the 10th term without having to use our hands. We can just use the formula and to also sum up some of the terms. And I'll get to these in a little bit. But what I want to do is just show you a few examples of sequences with ratios and try and work with me as I go through the sequences and try and get the ratio. So this is a sequence here with a ratio of 2. My second example might be 1, negative 3, then positive 9, then negative 27, dot, 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 dot. So this is an interesting one. It goes a positive, a negative, a positive, a negative. This is still a geometric sequence because our common ratio will be negative 3. Negative 3, negative 3. So R will be negative 3. So do look out for that. If you have a sequence that goes positive, negative, positive, negative, it will be a negative ratio because we know if we multiply a positive number by a negative number, it becomes negative. Then if we multiply that by a negative number, it turns back positive. So here is a sequence that has a ratio of negative 3. Okay, another example might be 32, 16, 8, 4, then we have a 2, 1, 1/2, 1/4, so on, so on. Now we have a sequence that's shrinking, it's getting smaller. And our ratio here will be common. Our ratio will be positive 1/2 because 32 times 1/2 is 16, times 1/2 is 8, times 1/2 is 4. So last one will be, let's go with negative 50, and then we'll have positive 10, and then negative 2, and then we'll have positive 2 on 5, so on, so on. Now this is also a geometric sequence where our ratio will be a negative fraction because it's going negative, positive, negative, positive. So it must be a negative ratio and it's being divided by 5 every time. So our ratio will be 1/5, negative 1/5 because we know that it times is by negative 1 on 5 to get to each new term. So hopefully you can see the pattern here for R. R, our common ratio, is any term, I'm just going to say U2 for now, over the term before it. So U2 over U1, it's U3 over U2, it's UN plus 1 over UN. This just means any term divided by the term before it. And just by taking our first example, 2 over 1 is 2, 4 over 2 is 2, 8 over 4 is 2, so we have a common ratio there of 2. Okay, so that's what a geometric sequence looks like. Now let's have a look at the first formula that the IB give us. If we want to find some future term, so let's use example 1. If we want to find the 10th term of this sequence up here, well, we know we can find the 10th term, U of 10. Remember, UN means any term, so U10 means the 10th term. By using this formula, U10 will equal U1, which is our first term, which in this case will be 1. multiplied by our common ratio, which is 2 to the power of, and it's n minus 1. Now our n for this example would be 10 because I want to find the 10th term, so it's going to be to the power of n minus 1. Okay, so u10 will be 1 times 2 to the 9, which we know will just be 2 to the power of 9, and we can work that out if we have a calculator or if your multiplication skills are on point. We know it's going to be 1, 2, 4, 8, 16, 32. This is the, and then 64, 128, 256, and I think we're going to get 512. So 512 will be the 10th term in this sequence here. Okay, now if we want to find the sum of a number of terms in a finite geometric sequence, so a finite sequence means that it might be a sequence that just keeps going up. See this one here, for example, 1, 1, 2, 4, 8, 16, 32. These numbers will continue to get bigger each term. 64, 128, 256. So every term will be a larger size. We can use this formula here. There's actually two of them, and it doesn't really matter which one you use. They're both the same formula. They've just slightly changed the order in which they write the r to the n minus 1 and r minus 1. Now, it does make it a little bit neater if you use the correct one, and it kind of depends on whether you have a positive or a negative ratio. But for now, it doesn't actually matter. You can just use either. Okay, so let's try and find, for example, the sum of the first and let's say 5 terms of our sequence up here. Now we could quickly do it in our head because this is a pretty simple sequence. 1 plus 2 plus 4 plus 8 plus 16. Well, this would be 24, 28 plus 2, 30, 31. So hopefully our answer is 31. But we can use this formula. So u1, which is 1. Our r is 2 to the power of n. We want to find 5 terms. Subtract 1 over r minus 1. So 1 times 2 to the 5 is 32. Take 1 is 31 over 1. So there we go. We've just proved our answer was 31. So this formula here helps us find the sum of a number of terms in a geometric sequence. Now, the last thing I wanted to point out is the sum of an infinite geometric sequence has its own little formula. Now, what this means here, the sum of an infinite geometric sequence, let me create some space, is that we do have sequences in geometric, in this geometric topic here, like this example here, example 3, where the terms are getting smaller and smaller and smaller. See how the terms started pretty big at 32 and then 16 and then 8, but then the terms became smaller and smaller because we had a ratio of 1/2. And eventually, well, the next term will be 1/8, then 1 on 16, then 1 on 32, and those numbers are becoming really, really small, and they will continue to get smaller. So if we're summing the number of terms in this sequence, for example, the sum of the first, let's say 1, 2, 3, 4, 5, 6, the sum of the first 6 terms here would be 32 plus 16, so 48, plus 8, 56, then 60, 62, 63. So the sum of the first 6 terms is 63. The sum of the first 7 terms will be 63 plus this half, so 0.5. The sum of the first 8 terms will be 63.5 plus a quarter, 63.75. And what you're going to notice is that as we go down here, even if we had the sum of the first 100 terms, it's going to be actually still be 63 point something, because these numbers that we're adding to the sum are so small. They don't have much impact to the sum. And it's going to be 63.99 something. And what this formula here says is that if we have an infinite number of terms, as we're adding the millionth term and the millionth and first term, it's just so insignificant, the size of those terms. If we sum an infinite amount of terms, we're actually going to get some number. And in this case, it should be 64. And we can use this formula to show that the sum of an infinite amount of terms will be u1. So for example 3, it was 32 over 1 minus our ratio, which is a half. So we'd have 32 over, now 1 minus a half is just a half. And how many halves are in 32? There are 64. So that's what this formula says. And we can only use this, the sum of an infinite geometric sequence, when the numbers are getting smaller and smaller and smaller. And that only happens when the ratio is less than 1, or actually it can be negative, but that the negative needs to be also less than negative 1. So that's how they write it here. This absolute value of r needs to be less than 1. That just means that r needs to be between negative 1 and 1. So negative 1 and 1. And if you have an r that's in this range, our terms get smaller and smaller and more insignificant. Okay, so this is just an introduction to geometric sequences and series. A geometric sequence is a sequence of numbers with a common ratio. The series is summing them up, and we're going to have some examples where r might be a small fraction and we have an infinite geometric sequence sum. Okay, good luck. Try some practice questions and try and apply some of this knowledge.